Well, good morning, everybody. Here we are again on a Monday morning. I apologize for the mess on Friday. I have no idea why it didn't record sound. Uh, I do this same setup every week. I don't touch anything, so I don't know why it had a hissy fit. Um, this week, we're talking about pressure versus gravity once again. You remember on the last video, we talked about atmospheric pressure. In this video, I want to talk about hydrostatic and lithostatic pressure. So my joke for the week, what is the reason for the stoplight turning red? Think about that. You haven't already read it. So a little review here, atmospheric pressure. Pressure is fixed at sea level. Everybody probably in the world knows 14.7 psi. It's also basically right at 100 kPa. I tried to keep my graphs in kPa and meters just for consistency. So this atmospheric pressure decreases gradually as you increase in altitude. And this has been proven time and time and time again. On Mount Everest, they have to have oxygen because the atmosphere is so thin. And other places like Machu Picchu and other places. This decrease in pressure as it decreases goes almost to zero at the highest altitude. So, we consider space as being a certain atmospheric pressure, and they call it the Kármán line. But the actual atmospheric pressure continues to decrease gradually until it gets almost to zero. You remember the infamous 10 to the minus 17 torr? You flat earthers need to realize your scientific numbers. 10 to the minus 17 is a teeny tiny number close to zero. So we have decreased our pressure practically to zero, and then we have the vacuum of space. So you don't have to worry about the atmospheric pressure being next to a vacuum because it decreases in pressure until the pressure is practically zero. You remember all the excitement of the moon suddenly being inside the atmosphere, and this is because of the geocorona. The geocorona extends out past the moon, and all it is an extension of the atmosphere, which is so thin that you can hardly measure the molecules. So it's composed mostly of hydrogen because the heavier molecules stay closer to the Earth because of what? Because of what? That's right, gravity. The data from this moon suddenly becoming inside the atmosphere was discovered by the SOHO satellite in 1996. That's like 13 years ago. So So let's talk a little about hydrostatic pressure. This is pressure inside the oceans. I think we all know, well, most of us know. Personally, I haven't been deep in the ocean, but I know a lot of people that have been scuba diving um, um, and other swimming, and you can feel the pressure increasing as you go deeper and deeper in the ocean. And in fact, it becomes dangerous as you go deeper. Uh, the equation at the bottom of this graph shows that at 0 feet, ocean pressure is the same as atmospheric pressure. So the atmosphere is pushing down on the ocean because of gravity. Um, I'm trying to keep reminding you that gravity is the force here. Um, so ocean pressure is the same as atmospheric pressure. If you notice at the top right of the graph, I have a little equation there. It's the equation of a line. Again, we should remember this from our high school algebra. The equation of a line is y equals the slope times x plus the intercept. So the intercept here is 100.4, which is the same as atmospheric pressure. And like I said, as the line crosses 0, it's the atmospheric pressure. The slope is roughly 10 kPa. So you notice that this slope, again, 10 kPa per meter. Keep that number in mind. The pressure here is a straight line, not curved like the atmosphere. And the reason for that is because the gas in the atmosphere is compressible by gravity, so it's curved. In water, liquids, anything in a liquid state is non-compressible, incompressible, whatever you want to call it. I found this YouTube video, guys. The title is Water Pressure is Affected Only by Depth, Not the Container Shape. So I thought that was interesting. There's a link. I can put that in the description. But still, pressure increases as we go deeper in the ocean. So just like in the atmosphere, uh, the more we go deeper, the higher the pressure. And why is that? Because of gravity. Lithostatic pressure. Lithostatic pressure is the stress exerted on a body of rock by surrounding rock. It is a pressure in the Earth's crust, somewhat analogous to the hydrostatic pressure in fluids. Lithostatic pressure increases with depth below the Earth's surface. So even the rocks in the crust have this same increase in pressure. And I guess unfortunately for us, because we're trying to see graphs, there are many types of pressure on a solid surface. So you have all these different pressures, hydrostatic, pore pressure, fracture, lithostatic, and those different pressures are caused by different actions. The lithostat, or the pressure in the rocks, is very complicated because the rocks are not uniform. They're different densities, different types of rock. Um, so, uh, so there are all kinds of different things going on. However, I want you to notice that the gradient for the lithostatic pressure, uh, the gradient is a constant 23 kPa per meter. So we can see that in the graph that it's linear. Again, solids are not compressible, so 23 kPa per meter. And once again, I keep repeating this, and I don't know how many times I can tell you that the only force acting on these rocks as we go deeper into the crust is gravity. So anytime we do an exploration or an experiment like this, there's almost always room for more study. Any scientific experiment you do, at the end of the publication, they'll say, I would like to study this if I had the funding or whatever. And so uh, there's always further study. So it was beyond the scope of this video. I could have talked for hours to discover the numeric relationship between gravity and these three pressures. So we did discover the slope of those lines, but there's a lot more going on there. In addition, it would be interesting to study the relationships between density and pressures. Note, and this is a very important note, density is a measurable property of whatever substance is looked at. It is not a constant force as gravity is. It is a measurable property. Just like you can measure mass, you can measure volume, you measure density. Density is not a force. Density depends on all these things. The biggest being the distance from the Earth's center of mass. And that's where gravity comes from, is the distance from the Earth's center of mass. So our joke of the week: what is the reason for the stoplight turning red? You'd turn red too if you had to change in the middle of the street. So this is my discussion about gravity and how it causes pressure increases in the atmosphere, in hydrostatic in the oceans, and the pressure in rocks in crust and deeper. So hopefully in the next 2 or 3 weeks, I hope I have an experiment where I'm showing you how gravity works, and I'm looking forward to showing that to you. We still have some things to work out, so keep your eyes open for that one. And I guess that's all for this week. Here's hoping that the sound works.